Hello everyone, my name is Martin Röck and I have the pleasure today to speak to you about our research at the Science to Policy interface, particularly the insights from a study supporting an EU roadmap for the reduction of whole life carbon of buildings. Specifically, I will be speaking on our paper for this World Sustainable Built Environment Conference, focusing on parts of the methods and materials, as well as especially the results that we get at building level as well as building stock level. There are a number of other results already published, most recently the technical report published through the European Commission, as well as a conference paper on the archetype selection process, which was published at the SBE conference in Thessaloniki. I invite you to review those documents if you're interested to learn more about what I'm talking about here. And I also invite you to stop this presentation at any point if you're interested to read along and see more of what is on the slides. For understanding this work, it's important to understand the role of embodied greenhouse gas emissions in the life cycle of buildings. As we could establish in previous meta-analysis that was published in 2020, embodied greenhouse gas emissions are really dominating the time frame for effective climate mitigation. The role of embodied carbon emissions has really changed. While in the past operational emissions were the majority of emissions in the building life cycle, it's now 50% or more of embodied greenhouse gas emissions. And furthermore, the temporal profile of these emissions is very different. While operational emissions accumulate over time over the building service life, embodied greenhouse gas emissions occur in spikes. And the largest of these spikes really occurs already before the building is actually in use. It occurs for the production of construction materials, the so-called upfront embodied carbon spike. And when we look at the emission profile, we see that this upfront embodied carbon spike really dominates the picture for 30 and more years. So certainly until 2040 and 2050, the emissions for new construction material production of new buildings really dominate the picture. We could conduct studies on collecting data and benchmarking embodied carbon across Europe, establishing representative or ranges and distribution of embodied carbon emissions for different building typologies, both residential and non-residential, based on the country collected from different European member states. What we could also find in this study is that the data availability is very different across Europe, even though there are some frontrunner countries which in that case could provide 50 case studies and more. We also saw substantial gaps across Europe. And filling these gaps and moving forward on the policy around whole life carbon and whole life carbon regulation was really one of the goals of this particular study, which was commissioned by the European Commission, DG Environment. Here in this study, we modeled the European building stock based on 4 regions and using representative archetypes to represent the different activities of existing building operation, energy retrofit, as well as deconstruction and obviously new building construction. We covered single-family, multifamily houses, as well as office buildings, and modeled these archetypes to represent different energy performance levels, as well as different material solutions. In this study, we deployed Karl Löwen's MMG model and the slice building LCA data format. This allows us to conduct a hierarchical inventory modeling, which ranges from the building material level up to the building level using a hierarchical approach where building materials are embedded in work sections, are embedded in elements, and are then constituting the buildings. We also captured a fairly comprehensive scope for the building parts considered, as well as the life cycle stages, which you can see here in green and orange. We then used the slice data model for scalable high definition life cycle inventory and LCIA results, which allowed us to capture this high detail of the building level data and use that for upscaling to the building stock. Conceptually, this upscaling takes place as I'm showing you here. The slice-based analysis really allows us to connect the spatial and temporal dimensions, where at the building level, we conduct this hierarchical inventory modeling as well as the impact assessment. We can then investigate the hotspots, the materials, the elements, and the life cycle stages contributing to the whole life cycle emissions. And we can also really map out the whole life carbon profile, the temporal profile of these emissions. We then scale this up to the building stock level based on the activity rates, the number of square meters being either newly constructed or being in use, being refurbished maybe, or undergoing renovations in a given year. Starting from our baseline year 2020, we could also project these activity rates into the future to investigate the evolution over time, and also understand and model the effect of different carbon reduction solutions, namely solutions related to avoiding new material use, for example, through material efficiency or through sufficiency related measures, as well as shifting to, for example, bio-based or other low carbon alternatives, and last but not least, improving conventional construction materials such as concrete or steel. Now, the results that we get at the building level show one thing very clearly. The advanced energy performance of new buildings really results in lower whole life carbon emissions. That's a very clear trend that we see in all regions and all building types that were modeled in this study. Obviously, there are different ways to achieve advanced energy performance, so to achieve low operational energy and low operational emissions. Some strategies are more, others are less material intensive, and clearly the less material intensive ones should be favored. What we see when we look at the whole life cycle emissions of our archetype specifically, we see that the embodied emissions make up, on average, 34% of buildings with new energy performance standard, new standard buildings, which are buildings representing current regulatory requirements. And for new advanced buildings, which are more like passive house buildings, we see that there are 74% of the whole life carbon emissions from embodied carbon. As mentioned before, these values can really range above 90% in extreme cases. Within the embodied emissions, we find that 84% are these upfront embodied carbon emissions that I was talking about earlier. When we dig deeper into our slice building LCA results, we can furthermore reveal different whole life carbon trends. We can benchmark the role of embodied and operational carbon, here shown by the results that we got for the new building archetypes for single family, multifamily, and office buildings, showing them for different regions and for different energy performance levels. We can also dig deeper and look at the embodied carbon contributions from different building materials as well as from different building elements. And a very interesting perspective that we also explored in this study is the relation of embodied carbon investment for renovations and the achieved operational carbon savings. And there we could see, for example, that while there is no clear correlation between the operational carbon savings and the embodied carbon invested, there is a clear trend which shows that the higher the annual operational carbon savings are, the lower the amortization period is. And we see that for highly effective energy retrofits, the amortization is usually already there within 2 to 5, at latest within 10 years. Now, when we go up to the building stock level, it's important to understand that this is done by scaling based on the activity levels. And here you can see for our baseline year 2020, the activity levels in the European building stock, where 97% of buildings were in use, in operation. Only 3% were something else, either constructed, or renovated. 1.5% were new constructions of different energy performance classes. But now when we look at the greenhouse gas emissions, the whole life cycle related greenhouse gas emissions related to these activities, we find that 50% of emissions arise due to new construction embodied carbon. So there is a factor of 10 for these new construction upfront emissions. When we look at the results in more detail, we find that even though 97% of buildings are in use, it's only 79% of operational carbon emissions versus 21% of embodied carbon emissions at the European building stock level. Out of those embodied emissions, 71% are upfront, so 71% are basically related to new construction. The other embodied carbon emissions are either related to renovation or to so-called in-use embodied carbon due to maintenance and repair of the existing building stock. So here it's important to understand that the majority of embodied emissions is really caused by just 3% of floor area. Those 3% that are undergoing new construction or renovation. Based on this baseline year, we then conducted the analysis of different scenarios, where we find that in a business as usual scenario that already considers the renovation wave, we see a substantial reduction of operational carbon emissions. However, there is not really any consideration of embodied carbon emissions in past policies. This is only now shaping. We find that it requires the application of a variety of solutions related to improving conventional construction material performance, as well as shifting to low carbon alternatives, for example, bio-based materials, to substantially reduce the embodied emissions, as well as a further increase in energy performance requirements and energy renovation rates to further drive down also operational carbon emissions. As you can see, only our life build scenario, which on top also adds the avoid solutions. These are strategies related to sufficiency or material efficiency, as I mentioned before. Only this life build scenario kind of gets us closer to somewhat of a net zero by 2050, but you see there is still a substantial gap. We still find that 344 megatons of CO2 are remaining in 2050, so more ambition will be needed to effectively decarbonize the European building stock. What we could do with the detailed data that we established here is to also investigate, on one hand, on the left side, as I said, the contribution of different life cycle stages to the overall life cycle emissions at the building stock level, again showing the important role of the new construction. But we could also compare, for example, the embodied carbon at material level in our business as usual scenario here, comparing 2020 to 2050 material embodied carbon emissions, and we see that there is hardly any change in the production stage for new construction, but there is a substantial change in the embodied carbon of refurbishment, where we see basically the effect of the renovation rate, which asks to at least double renovation rates. This is also mirrored here in an approximate doubling of embodied carbon emissions for refurbishments. Again, here it's important to keep in mind that these embodied carbon investments are very effective and usually pay off within a few years due to improved operational carbon performance. Now, when we compare the results that we get through this building stock modeling with the carbon trajectory and the climate targets of the European Union, we find that not even the life build scenario really delivers carbon reductions at the rate expected for the whole European economy. So that really tells us that at a minimum, reductions according to the life build scenario are needed to stay within reach of the climate targets for the European Union. And climate neutrality really requires further action on reducing and removing carbon. When we bring these results back from the building stock level down to the individual building level, we can also map out what the values per square meter of building floor area are that we got in this study. And here you can note that we show the average values as well as the best practice that we modeled in our archetypes. These are changing until 2040, where we assumed that the solutions would be fully implemented. And you can see that the average embodied emissions fall and the intermediate target values are possible within existing materials and design approaches. Furthermore, also for renovations, the embodied emissions fall, but there we see that we did not capture the full potential for reducing those emissions due to limitations also in the solutions considered. The key takeaways of this study. 1. Embodied carbon is still, and also in Europe, the hidden challenge for effective mitigation of climate change. Many solutions are readily available to reduce embodied carbon and whole life carbon emissions of the European building stock. However, for the European Union, it means more and a more holistic effort is required. We need to continue to decarbonize space heating, implement high renovation rates and high renovation depths. There is a clear need to further improve, shift, and avoid construction material use, for example, through circular cascading use of bio-based materials and conventional materials. And we have a very clear indication that sufficiency now is really key to reducing emissions in the short term. So, for example, through the use of existing buildings, which then also leads to reduction of new construction rates. To generalize this a bit more, we really see that Europe, as a representative of the global north, here our challenge is to really put all hands on deck to deliberately shift resources from new construction to energy retrofit. This is very different from a global south perspective, where we see the need for additional construction to really ensure well-being. And there, I think the task is to shift and improve construction to enable a just transition of the built environment. As an outlook to this study, I also want to share with you our current work that we're doing for the European Commission, this time for DG GROW, in an extended consortium. I invite you to learn more about this study through the link or the QR code. In this ongoing analysis of greenhouse gas emissions of buildings and construction, we're investigating both the current data situation and how to improve it, as well as analyzing life cycle related greenhouse gas emissions and removals of buildings and construction across Europe. I thank you very much for listening to this talk. Feel free to get in touch. I'm looking forward to hear from you. Thanks again.